In this video we will show you how to demodulate a train of pulses with a Schottky diode detector. We will also see how to use the sweep mode and the pulse mode on our mini-circuits generator. Let us generate a radio frequency signal with a frequency f sub c. The period will be the inverse. I will call x to this signal. Omega sub c is usually called carrier frequency. And I want to detect it with a Schottky diode. We know that we will obtain at the output a DC voltage. Let us assume that we want to monitor this voltage with an oscilloscope. Of course, the oscilloscope will display the output of the detector, which is just a DC voltage. We are using a diode with reverse polarity, and therefore we can see that this voltage is negative. We know that the higher is the input power, the higher will be the observed voltage. I will check this with a small experiment. I have connected the Schottky detector to the output of my mini-circuits generator, and I will use the sweep mode. So I go to sweep mode, select power sweep, and specify a start power of minus 30 dBm and a stop 10 dBm, 2 dBs of a step, and I set the frequency to 1000 MHz, and finally I specify a dwell time of 1 second. This parameter is the time the generator will keep supplying each voltage level. I activate the free run trigger and then apply the power. The generator applies first the maximum level, come back to the minimum and start to show the different voltage levels for each applied power. So we are going now in 50 millivolts, now 120, 170, 300, and the maximum voltage is around 600 millivolts. Now I want to figure out what would happen if I apply to my detector a train of pulses with a duty cycle of 50%. This means that the duration of each pulse will be 50% of the period. We will call Fm to the corresponding frequency. This is usually called modulating frequency. I can easily write an equation for this signal with the aid of the sine function. This is very helpful to generate samples of square waves. This signal is indeed a signal modulated in amplitude, where the transmitted message is just a square wave. It could represent a sequence of ones and zeros. If I apply this signal to a detector with the output connected to an oscilloscope, I should expect to see just a square wave. Let us see what happens in the real life. So I go to the option Pulse Mode and specify a square. Our modulating frequency will be 1 kHz. I am going to use the minimum nominal power for the detector, which is minus 30 dBm. Let us see if our oscilloscope will be able to measure the resulting output power. I press Run Pulse and oof! It seems that the signal is too weak, and yes, the vertical scale is at maximum resolution. It is at 2 millivolts per division. Obviously I could increase the output power, but just a minute, maybe we can find more elegant choices to see something. I have used the default configuration of my oscilloscope. Maybe I can improve the detection by changing something here. Let us press the channel button, then I go to coupling and specify DC. Good. The things have improved quite a bit. I have simply changed the input impedance of my oscilloscope, which was 50 ohm. We are not displaying a radio frequency signal, but a square wave of 1 kHz frequency. The detector output has an impedance of about 1 kΩ at this frequency. Therefore, if I want to properly measure the voltage at the detector output, I need an oscilloscope with an input impedance much larger than 1 kΩ. 1 megaohm is perfect for this, but I can do more. Now I go to the option bandwidth and specify the minimum one, 8 kHz. What happened? My oscilloscope is a very expensive one. It has an impressive bandwidth of 1.5 GHz, but obviously I don't need this bandwidth to detect a square signal of only 1 kHz. Using a measurement bandwidth much larger than the signal bandwidth, we are just obtaining a very poor signal-noise ratio. Very nice, but let me show you one more trick. The signal is quite stable, so I go to Acquire, Mode, and specify Average. Not bad, our oscilloscope was able to measure amplitudes corresponding to the minimum nominal input power of our detector.